Alright, howdy howdy AP Physics students. Today we are going to be starting our unit on dynamics. And in order to do that, we are just going to start with Newton's laws. This is going to be a quick lesson about Newton's laws of motion and a couple applications of how to use it. Alright, we're going to start from the beginning. We're going to start with Newton's first law of motion. Newton's first law of motion states that an object in motion will tend to stay in its current state of motion unless compelled to change by an external force. So an object in motion will stay in motion, an object in rest will stay at rest. So some sorts of external forces that can change an object's motion will be things like gravity, like we saw in our projectile motions questions. We saw that it made it go in an arc instead of just going in a straight line. And then another thing is friction. Now friction is something that's basically going to resist the movement of an object on a surface, and we are going to get to that in our next lesson. So, another important thing to note with Newton's first law is a property called inertia. So inertia is just an object's natural resistance to changes in its motion. And this is why Newton's first law is also commonly referred to as the law of inertia. Because objects, they don't like to change their motion. No, they do not. So let's take a look at this first example. What net force is required to maintain a 5,000 kilogram object moving with a velocity of 7,500 meters per second? Now, keyword here is maintain. Because it's maintaining it, that means that it's already going to be moving at 7,500 meters per second. So, because that object is already moving at 7,500 meters per second, the law of inertia states that it's going to keep going with that same speed without any extra force being added. Now, you might be thinking, well, that's weird. How come I have to keep stepping on my accelerator? I can't drive. How come I have to keep stepping on my accelerator in the car to keep it going at the same pace? If I take my foot off, my car is going to slow down. That is because of the way cars are made. You need to keep adding that extra force to keep the car moving. Because there's a lot of friction in the road that's going to be stopping it. There's a lot of friction going along in the gears inside your car that is going to resist the movement of your car keeping going. So you need to keep adding that extra acceleration. But if friction wasn't a thing and air resistance wasn't a thing, you could just step on your accelerator and your car would just keep going the way it is. So, yeah. In this example, we're assuming that there's no friction, there's no air resistance, none of that. Which means that it's just not going to need any extra force to keep going. Now, we are going to move to Newton's second law. Newton's second law of motion states that an object's acceleration will be, I didn't write that there, but it will be directly proportional to the strength of the net force and inversely proportional to the mass, or as we most often see it, force equals mass times acceleration. Now, another thing I want you to note here is right here. We have our unit for force, and that is going to be a Newton. That N stands for Newton. So 1 Newton is going to be equal to 1 kilogram times 1 meter per second squared. So when you're working with questions about force, you're going to want to convert everything to newtons, kilograms, and meters per second squared. Now, because our mass is a scalar, which means it just doesn't have a direction to it, the direction of the force is going to be the same as the direction of the acceleration. So if an object is accelerating to the left, the force is going to be going to the left. Now, let's look at a second example. How much force is required to cause an object of mass 2 kilograms to have an acceleration of 4 meters per second squared? So we're just going to plug this into Newton's second law of motion. Force equals mass times acceleration. Our mass is 2, and our acceleration is 4. So we have force equals 2 times 4. Our force is going to be 8 newtons. Now, one common thing you're going to see a lot of in Newton's second law is weight. This is going to be one of your most common applications. So weight, contrary to popular belief, is not the same as mass. Mass is the amount of matter in an object. Weight is the force of the gravity on said object. So in order to find our weight of an object, we can substitute in g for the acceleration. So our force of gravity, or this is also more commonly written as force of weight, so F sub W, is equal to mass times gravity. Alright, and now we are going to be going on to Newton's third law of motion. This states that for every action there is an equal yet opposite reaction. So you have the force of object 1 on object 2, is equal but opposite to the force of object 2 on object 1, this here is just showing that those forces are going to have an equal magnitude, but they are going to be going in the opposite direction. So let's say you run into a wall. I've done that. You run face first into a wall. Whatever force you running face first into that wall exerts on the wall, it's going to come right back at you in the direction you came from, and that wall is going to exert a force right back on you. The force of object 1 on object 2 and the force of object 2 on object 1 are called an action-reaction pair. Now, a really common way you're going to see this is with normal force. So, when an object comes into contact with a surface, the surface exerts a force on the object that is equal and opposite to whatever the force of the object is applying on the surface. And this normal force is going to be perpendicular to the surface. So let's take a look at an example for that. A book whose mass is 2 kilograms rests on a table. Find the normal force exerted on the book by the table. So, we are going to start by drawing a picture. Here's our picture. This is going to be our book. This is going to be our table, and we are just going to draw, this is kind of like a free body diagram. You're always going to want to draw free body diagrams when you're working with force, just so you know where everything's going. And this is especially going to come in handy later when we're working with our simple machines, or when we're working with our pulleys and our inclined planes. Trust me, you're going to, especially when you're working with friction too. You're definitely going to want to look at it when you have all of these different forces acting on an object, just so you know what direction things are going in. Anyways, let's go back to this example. So we have our book, we have our normal force going up, see how it's perpendicular to the surface, and we have our force of gravity going down. So, we know the force of gravity, and we know that the normal force is going to be the same magnitude, so we're going to solve for this gravitational force. We have the force of gravity equals our mass times gravity. We know our mass is 2 kilograms, and the gravitational acceleration is going to be 10 meters per second squared. So, what this is going to look like is we're going to plug it in, and we're going to get the force of gravity is going to equal 20 newtons going down, which means that our normal force, since it's going to be going in the opposite direction, perpendicular to our surface, is going to still be 20 newtons, but it's going to be going up instead of down. Let's take a look at example 4. An object feels 2 forces. One force is pulling 8 newtons to the left, and one force is pulling 20 newtons to the right. The object's mass is 4 kilograms. What is its acceleration? Once again, we're going to start by drawing a free body diagram. So we have this force going to the left, and it's 8 newtons, and we have this force going to the right at 20 newtons. Notice how I drew this force bigger than this one, because, well, this is a greater force. It's going to be going that way. So in order to do this, we have to find our net force. So our net force is just going to be the force of the object when it eventually goes in the directions it's going to go. And in order to do that, we need to subtract our smaller force from our bigger force. So we're just going to subtract 8 newtons from 20 newtons to get our net force. And our net force is going to be 12 newtons going to the right. Alright, and now we're just going to plug this in to our Newton's second law. So we know force equals mass times acceleration. Our force is 12, and our mass, as stated in the example, is going to be 4. So we're just going to plug this in, and we are going to get that our acceleration is 3 meters per second squared. Alright, so in this lesson we learned Newton's laws of motion, we learned the law of inertia, force equals mass times acceleration, and for every action there is an equal yet opposite reaction. We learned about the normal force, which is just the force exerted back onto an object from a surface. It's always going to be perpendicular. We learned the difference between weight and mass. Weight is going to be the force of gravity, and mass is the amount of matter that's in an object. And we learned net force on an object. Ignore the fact that I wrote net force twice. We learned the net force is just the force of the eventual total force that ends up being put onto an object. So I hope this example and this lesson helped you learn about Newton's laws. This is going to be the very foundation to our dynamics unit, and we're going to come back to this a lot. We're especially going to come back to weight, normal force, and Newton's second law. Those are going to be incredibly important. So, I hope this is helpful, and the link to this the link to this Google slide should be in the description, and I hope you guys, I hope this was helpful. Cheers!